So thank you everybody for joining for our third week of the Tales from the Testbed. Had another great group of forecasters this week from across the country, and had a little bit of weather to talk about this week, a little bit more so than last week. All right, so first a little bit about the EWP. So a lot of you are probably familiar with the EWP, but just if there's someone on there that's not, we focused to improve prediction of severe convective weather events at the warning scale, looking at various experimental products and even some operational products, just how those can be better incorporated into an operational environment by inviting forecasters like the ones here this week to evaluate these data in an operational setting. Also being located in Norman, have a large group of researchers, operational meteorologists, and students, and as well as lots of industry around to facilitate some of that research that we see in the test bed throughout the weeks. Aim to serve all the WFOs and CWSUs across the National Weather Service, and really consider this a vital component to transition these research that goes on into operations, and also getting operational feedback to transition back to the research and development that goes into these algorithms. So this week we operated in a few CWAs across the country. So we started out in the Norman and Lubbock and Amarillo areas. Also operated in San Angelo, Texas, up into Rapid City, South Dakota yesterday, over into Little Rock, Arkansas. Also operated on Tuesday up in the Northeast, across Philadelphia, Albany areas, and also operated in Sterling to begin the week. So with that, I'll hand it over to our presenters, and first will be Mike Johnson from WFO in Memphis.
Well, good afternoon. First slide that I wanted to do, I wanted to show here was talk about the GLM a little bit, and the ability to sort of discriminate anvil lightning from the other various forms of lightning. The GLM does show the aerial extent of lightning better than the ground-based networks such as the Earth networks or NLDN. Whereas the surface-based networks, they show points and not the aerial extent. So the way that we've been trained, in my career over the last 15 years, one flash, 1 point, versus several pixels possible in the GLM data. So it's sort of a different perspective, a new paradigm for viewing this data. But in this particular slide, I've got the Earth networks data up in the upper left, and in the upper right, we have it's called flash extent density. You can sort of see the aerial coverage of the particular lightning strike, which is actually extending a good couple of counties north of the cluster of lightning. In the lower left-hand corner is the average flash area, and you notice the very high values, which can show the size of the flash. And in this case, this is sort of a good indication of anvil lightning, which is extending again much farther north than the cluster of lightning that you see in the upper left-hand corner that we're used to looking at. And I find this to be particularly useful for IDSS purposes. Where we've got maybe responders out in the field, or there's events going on, and we can sort of judge that aerial extent a little better than what we could with the point data. Go ahead, Mike. The second slide here is a way to view the lightning trends. We can always run through the lightning, the flash extent display on the GLM there. We can run through the density there and loop it, and we can sort of gain a trend from it. But using the tracking meteogram tool, I was able to create the trend table over on the right, and we've got several different fields that are not shown on the particular image on the left. But it's a good way to visualize lightning jumps, detect when the lightning really begins to taper off, as opposed to going through a loop and trying to kind of quantify it in your head as it moves through time. This does it for you. The third slide here, the GLM data, like other lightning data, does provide a sort of a lead time when it comes to developing convection. In this case, we've got convection developing aloft to the south of the main line there, and we can really see a jump on the right side of the flash extent density. And that occurs well before the core develops in the lower levels. So that gives us an additional 5 to 10 minutes of lead time here before we begin to experience the stronger convection at the surface. And finally, I want to talk about the parallax issues that we have with the GLM data. Of course, farther north, farther west you get away from GO16, the more pronounced it will be. But in this particular case, the yellow lines indicate the CWA boundaries. And you notice in the upper left-hand corner, the flash extent density, as well as the other products, do extend across the CWA border into the Amarillo forecast area. Whereas if you look at the point data in the lower right, it's displaced a good 15 to 20 miles to the southeast. So that's going to be something to keep in mind, when you're talking about lightning entering a certain perimeter, maybe to an event or a venue where you have notification purposes for IDSS. And you also want to keep in mind that flash extent density may actually be accurate, but the Earth Network's data is got to put that point somewhere instead of representing as an aerial coverage. But the parallax issue is something that you need to keep in mind when you're looking at the data. So my takeaways from this week, the various GLM products really do help you see the aerial extent of the lightning data far better than the ground networks. I mean, we can always kind of visualize the point data and sort of draw contours around it. But the GLM data kind of does that for you, and it's just one less thing that you really have to worry about. It's a quick overview. We noticed increases in flash extent density prior to the intensification of thunderstorms in the low levels as the core was developing aloft, and we begin to see the discharge. So that gave us a little bit of lead time there. And don't forget to account for the parallax error when you're looking at the data.
All right, thank you, Mike. So next will be Gary Canalti, he's going to be our broadcast meteorologist for the week from Madison, Wisconsin.
Thanks, Michael. Good morning, good afternoon to everyone. As a broadcaster, I was really interested in the products that could help me in the very short term, or actually when severe convection was going on. So while things like new caps and the all-sky were great in setting up the overall situation, I thought things like GLM, the Prob Severe, and the CI would help me the most. And fortunately, the first 2 days I had basically linear convection, squall lines in the northeastern part of the country, and then the last 2 days I was dealing with some air mass thunderstorms in West Texas, and then the convection around Rapid City, South Dakota. So as you can see, this is the loop of the CI probability at the tail end of that squall line on Tuesday, pushing through southern Pennsylvania. The probabilities appeared highest at the tail end of the squall line, much as where you would expect additional convection to take place, and within the next hour that line of storms easily extended into northern portions of Maryland. Where the CI probabilities did not work as well, you can see some convection over the northern portions of Virginia, farther to the south. Not sure what caused why it was so low there, even before this loop started. Just very low probabilities there, if we saw anything at all, and that could have been some of the topography there just causing the thunderstorms to develop. And then also to the southeast, from about Richmond, Virginia, over toward the Delmarva Peninsula, or even farther south there, you can see some probabilities popping up there, and nothing really developed in that area. And then finally to the northwest, behind the squall line, where the clouds broke, the sun was able to come out and heat the lower levels, you start to see some development there. It'd be nice to know if there were areas where you could expect a little more in the way of convective development. And as you can see, the probabilities just kind of jumped all over the place and really didn't pinpoint an area where you would expect something to pop. Go on to the next loop, please. This is the same loop. This is with the probability of severe convection. And here, and this is something we all noticed, is that you can see those probabilities going up and down and coming up and down. Sometimes they were at higher levels than just the plain CI product. So it really didn't make much sense in seeing that you had a high probability of severe convection and yet a low probability of convection itself. You can also see that down to the south in Virginia. Again, nothing was developing in that area. Go to the next slide, please. So this is West Texas the following day. We were expecting storms to develop. You can see in the lower right corner, visible satellite imagery, starting to see some cumulus development there. Radars in the lower left corner. Upper left is CI, and upper right is CI severe. And again, those values were jumping all over the place for CI severe. In CI, you can see maybe there would be something starting to develop over the southeastern portion of the county is immediately west of our CWA. But if you go to the next slide, you can see where the convection actually started to develop, farther back toward the north and west. Again, if you look in the upper right corner, it's showing high probabilities of CI severe. In the northeastern portion of the county, nothing was going on there. And then you can see exactly where the convection was developing. Started to get a little convection in the northern part of the county. What was interesting was as these storms developed to the southeast, they became severe as they moved into our CWA. One of the largest hail reports, though, was actually just north of this county as the convection started. And again, the CI probabilities didn't show anything, especially the CI severe probabilities didn't show anything there. So we go on to the next slide. So by yesterday, I had looked at the CI probabilities. It didn't show anything, and yet here we had a supercell storm that developed pretty rapidly right on the Wyoming, South Dakota state line. GLM lightning data was very helpful in predicting that this storm was going to ramp up. If you go to the next slide, you can see also the visible satellite imagery, very clear that convection developed there. But again, the CI product didn't do very much at all in predicting where that supercell was going to develop. So if you go to the takeaways, I had high hopes, I think, for the CI product, but it just seemed to work best where we were expecting convection anyway, and it didn't do well where you needed it the most, where the initial convection was going to take place with air mass storms. And the CI probabilities didn't work well at all, and just didn't make any sense. So we had really very low confidence in that. In the end, I thought the GLM and the Prob Severe products gave me a better idea than the CI as to where severe convection was going to take place. That's all I have.
Thank you, Gary. Next will be Patrick Bach from the WFO in Central Illinois.
Thanks, Michael. The products I'm focusing mainly on are the All Sky product and the NewCap product. And one of the most important things we do when we're doing short-term forecasts or nowcasts of convection is you need to do mesoanalysis where you're monitoring trends, and then as things change, you adjust your expectations. And we need to having as much real-time data as possible helps us in that regard. And both of these products were very useful, I thought, in helping to assess trends. This day we were doing forecasts. This is Monday. We're doing forecasts for the normal Oklahoma area. We had some convection up to the northeast in the vicinity of Kansas City, and then there was some also over towards the Texas Panhandle. There wasn't a whole lot going on in between, but we did have a distinct boundary there. You see just a little bit of a Q field, but nothing too significant over Norman's area at this point. So if you go to the next, you can see the All Sky lab cape shows a very significant high cape value over a good portion of the Norman's area, and to the northwest of there, there was definitely a dry line or a cold front separating the two areas there. Within that cape area, I took a NewCap sounding. On the next slide, you can again shows very unstable air mass over that area, and they were generally in fairly a good ballpark. They had similar values. NewCap soundings overall seemed like their cape values overall tend to be a little bit lower than what we were seeing with the All Sky. Go to the next one. And this is our next day. We were over Lubbock, and this one I picked this because it showed a really distinct gradient in the cape across the central portion of the forecast area from north to south. We were monitoring some general tower and Q building up to the western portion of the CWA, but nothing was really getting going. And monitoring the evolution of the cape, you were able to loop the cape. You were able to see with time as the storms moved over the higher cape area, as you would expect, they started to take off. So being able to see as these convective elements were moving into a more unstable area, how they were able to take off from there. I did do another sounding within that area, and again, you saw where there was significant case, and then the cap was gone. And the timing on these soundings, the new cap soundings, is pretty useful. And through the central part of the country, it looks like they come oftentimes in the middle part of the day, and sometimes you might have a special 18V sounding, or there's been many hours since you had your 12V sounding. It's kind of nice to be able to get a look at how things may have changed in the vertical, what the kind of cap looks like outside of a normal rayout area, and I thought this was useful in showing that. This is next day as we were at St. Angelo, and nothing really exciting from a boundary standpoint. Just over St. Angelo, just a fairly general, moderate cape in the area. Overall, I'd say it was giving about 1,500 joules per kilogram over the area. So I did do a sounding in this area with the new caps as well. The first one that came out, this was the improved latency, the first one that came through, and this one this was a day there was a pretty stark difference between the soundings. We were only getting the capes on this were only on the order of a few hundred as opposed to 1,500 on the all sky lap. So my question is, what was the big difference? It seems this day that there was some trouble. The new caps had some trouble modeling the boundary layer a little bit. That modified new cap sounding, which did come in a little bit later, seemed to have a much better feel. It was closer to what the all sky had, and it seemed to be more what we would have expected based on the model guidance. Okay, and I apologize for the jumpy loop here. I did take out the black frames when I made the loop, but I guess when it converted to a GIF, put them back in. But this was yesterday. I thought this was the surface to 900 millibar, the lowest layer in the all sky precipitable water layer, and it really showed well where the dry line was, and putting that in a loop, you were able to see, along with the surface observations, you were able to really see the movement of the dry line, which is what we were keying in on for some of the convective enhancement over our area yesterday and the Amarillo's area. So just being able to see these changes with time, using real data as opposed to just model data, gives you some more confidence in that regard. So overall, the takeaways is, I thought the all-sky lap and new cap products are very useful for assessing the pre-storm environment, especially outside of our rayout times, and it's nice to get new actual data in there that can give you an idea of how things may have changed from the morning. If you need to adjust your forecast, maybe the cap was stronger than you expected, or whatnot. And overall, thought the all-sky products did look pretty well as far as, especially when you're looking at the gradients. Maybe the absolute values weren't perfect, but the gradients were generally where you would expect them to be. There was one yesterday. I was able actually to compare them, because there was an Amarillo did an 18Z sounding yesterday, and it wasn't too bad. It was generally lower. Like the instability generated was lower than what was in the actual rayout, but it wasn't too bad. New caps, same thing. It seemed like in general it tended to underestimate instability, but it still gave you an idea, and it was nice to have a sounding outside of your normal rayout time. And between the two options on the new caps, that improved latency, and then the modified, which comes a little bit later, the modified did seem to have. It wasn't consistent. Some days it was they were similar, but some days the modified sounding did appear to do a better job with the boundary layer. And even so, using the tools within ALIS, you are able to modify the new cap sounding just like you could modify a model sounding. So it's definitely useful for getting an overall feel for how things are going. So also with the one thing with the all sky was that it tended to the instability and the moisture profiles looked a little bit better than they did in the baseline, the GOES stability parameters. It seemed like they had a little better handle, and it was also nice to have the cloudy area holes filled in, with using the all sky algorithm.
Right. Thanks, Pat. So our last presenter for this week will be Al Cope from Mount Holly.
Okay, well, I just have a few slides here, but the product I'm going to talk about here is the Prop Severe, and of course this is not a new product. Most of you have probably seen this and used this in operations. Basically, it gives the probability of a storm producing severe weather within the next hour or so, and it uses inputs from radar, satellite, lightning, and numerical model. It's a combination of various parameters. And it's a good to use kind of in a relativistic sense, I think, to identify storms which stand out from the others, maybe doing triage, identifying storms that need further investigation by radar, and it's good for overall situational awareness. Okay, so now what's new here at the testbed this year is that not only are we looking at the overall severe probability, but we're looking at three subcomponents of that, which is kind of illustrated in this floor panel here. You have in the upper left is the overall prob severe. In the upper right is the tornado probability, and in the lower left is that's the hail probability, and then in the lower right is the wind probability. So you have these three components, probabilities of wind, hail, and tornado, in addition to the overall probability. And the overall probability in the upper left is essentially just the maximum of the three other ones. So let's see, and another thing that's new this year is that there's one of the products that's included is the AVI imagery from the GO-16 satellite, which of course is available more frequently at least every 5 minutes. So that in general will give you a better depiction of the cooling clouds with the thunderstorm tops and the growth rate of the storm. So that should be a general improvement to this product. Of course, and when we issue warnings, we want to include information specifically about the likelihood of hail or winds. We would like to try to distinguish between the two if we can, and also, of course, the probability of generating a tornado. That's probably the most important distinction, tornado versus non-tornadic. So that's the potential usefulness of separating the probabilities into these different components. So let's go to the next slide here. Now this is the line from Tuesday that was the squall line, or QLCS, that moved through the mid-Atlantic, northern mid-Atlantic, and into New England. So you can see the different probabilities. This is the overall probability, I believe. And you can see the different cells. This illustrates one of the difficulties in that you can see that it's not consistent in identifying cells, that some of the cells merge and then they split, and then some of the ones, like especially down on the trailing southwest end, you tend to get very long objects identified. And that's partly because it's using your overall reflectivity, combined reflectivity, to identify the storms. We talked about potentially using reflectivity at a higher altitude, maybe at the minus 10 degrees sea level, to better identify the stronger storms. There would be a slight drawback there would be a slight increase in latency, maybe about 1 minute, but I think that might be worthwhile if it can better identify individual storms, because that would affect all the overall probability in each of the three tornado, wind, and hail probabilities. One more thing, the tornado probabilities were, as you would expect, were generally a lot lower than the hail and wind. But in this one case, this is on Tuesday again, Looking at some individual storms that developed out ahead of the main line across southeastern New York, in this case, the tornado probability is in the lower right panel. You can see that one storm there has a probability of about 85% of tornado development. And that was a bit of a surprise because we were expecting tornado probabilities to be quite a bit lower, and you would look at a relative sense and say, well, if it went up from 2% to 30%, that would be a significant increase. But here, you know, lo and behold, we have 85% is almost comparable to some of the others. So that certainly draws your attention. And I don't know if that particular cell produced a tornado, but I know there was some storms just a little bit south of there that were outside of the Albany CWA that we were working on that day. So I know some of those storms did produce tornadoes across southeastern New York and into Connecticut, I believe. So that's surprisingly strong signal from the tornado probability in that case. So it is capable of doing that under the right situation. Okay, so finally my takeaways. This year we have the experimental separate probabilities for wind, hail, and tornadoes, as well as, you know, just the overall severe. It's best to probably use it in a relative sense and to indicate which storms deserve further interrogation. I didn't really get a chance to carefully compare probabilities for wind and hail, but I would say in general the hail probabilities did tend to be higher than the wind probabilities overall. And tornado probabilities were generally much lower, but in certain cases they could be very high and equivalent to wind and hail probabilities, like the last slide I showed. And then finally, an area for improvement is the way to more consistently identify individual storms, particularly within a cluster or within a line of storms.
All right, well, thank you to all our presenters, and I'll leave this last slide up here if you're looking for any more information on the test bed or the experiment for this year. You can go to those sites there and learn some more.